We're ready for part C. In part C, we are at 15 milliliters, so we're not quite to the equivalence point yet. It's going to be located on this chart somewhere in this area, maybe around here. We're still in the buffer region. This would have been 10 milliliters. This is 20 milliliters, so we're halfway between the two at 15. So we'll say we're right here. Okay? So that is what we're going to be working on with this problem. So we will once again start with our reaction so we can do our work. The first reaction you need to write is the reaction between the weak acid and the strong base. Do not include your sodium hydroxide. It'll just get in your way. Use OH minus to represent that strong base. Give yourself room for an ICF table. Know that in this table we will plug moles into the equation. To obtain the moles of each of these substances, we just need to remember that moles is molarity times volume. So for the moles of HA, it's exactly the same as the previous problem that if you watched part A, but so I'll quickly go through the numbers. 0.249, that's the moles per liter of the butanoic acid, and we had 20 milliliters, and that's 0.02 liters. That's going to give me 4.98 times 10 to the minus 3 moles. This will go in this spot right here. 4.98 times 10 to the minus 3. The number of moles of sodium hydroxide, actually hydroxide is what I want, so that would be the same as the number of moles of sodium hydroxide. This number will not be the same as we did in part A. We're adding more. So we take our molarity of 0.249 moles per liter of the sodium hydroxide and we multiply by the 15 milliliters or 0.015 liters. This will give me a value for the number of moles of hydroxide of 3.74 times 10 to the minus 3. And I can put that value into my table. 3.74 times 10 to the minus 3. Again, there is no A minus yet, and we don't worry about the water. The smaller of the two will get consumed, so I will consume the 3.74 times 10 to the minus 3 of the hydroxide and carry that across every part of this ICF table. We know that for every 1 mole of hydroxide you react 1 mole of NaOH, so these two numbers have to be the same, and you produce, according to the balance equation, the same amount of the product. So that will give me a 0 here. I have consumed all of the hydroxide. It will leave me with 1.24 times 10 to the minus 3 moles of HA, and of course produce 3.74 times 10 to the minus 3 moles of A minus. Once again, I see that I have present some weak acid and some of its conjugate base. So once again, this is in a buffer region. It is a buffered solution. And I can use the Henderson-Hasselbalch equation. pH equals the pKa, which is the, I'll go ahead and write the equation, plus the log, number of moles of base over number of moles of acid. So pH is equal to the negative log of 1.54 times 10 to the minus 5. That part is the same as in part B, plus the log of the number of moles of the base. That is this value here, so that would be on top, 3.74 times 10 to the minus 3, and 1.24 times 10 to the minus 3 is on the bottom. When you do the calculations here, you end up with a value of 5.29 for your pH. Now, if we compare that to the previous problem, part B, we're going to see that the pH did rise. It was 4.812, and now it's 5.29, so it did go up, but it didn't go up a whole lot.